So last time, up to now, we have discussed statistical mechanics and how we derive thermodynamics from microscopic considerations. And we have seen that depending on the type of systems we are considering, there are different descriptions. The microcanonical ensemble, when the energy is fixed for an isolated system, or the canonical ensemble when for a system in thermal equilibrium with the environment. And so we have seen that for the microcanonical, so for isolated system, the variables are the number of particles, the volume, and the energy. And because the energy is constant, these are fixed. And the relevant quantity is the entropy. And we have seen that we compute the entropy by computing the number of microstates which are consistent with the macroscopic state specified by these variables. Okay. Now, and this is called the microcanonical ensemble. No. And if we have a system in thermal equilibrium, then the relevant variables are the number of particles, the volume, and the temperature. These are fixed. Whereas the energy fluctuates. And the relevant quantity here is the Gibbs, the Helmholtz free energy, which is minus kT times the log of the partition function. And this is the canonical ensemble. Now, pretty much as what we have done here, we would like now to consider systems where also the number of particles is not fixed, can fluctuate. Okay, and so systems which are not only in thermal equilibrium but also in chemical equilibrium with a larger system. Okay, and so for this system in thermal and chemical, so the variables which will be fixed are not N, V, and T, but the chemical potential, the volume, and the temperature, because we know that if two systems can exchange particles and are in equilibrium, then the chemical potential of the two systems will be the same. This we know from thermodynamics. So these variables will be fixed, and the energy and the number of particles will fluctuate. And then we want to we ask ourselves what is the analog. What is the analog of the Helmholtz free energy, and more importantly, what is the analog of the partition function? So, what is the quantity that we should compute from the microscopic dynamics of the particles, which will allow us to derive the thermodynamics? Okay. So, and this is so the ensemble which corresponds to this is called grand canonical. ensemble. So this is what we are going to do today. So this is not only why it is important to have such descriptions. First, if you want to consider systems which are in chemical equilibrium, but also if you want to consider systems, for example, at phase transition, which are in where there is a phase equilibrium. So you may have the same substance, the phase transition point, which is maybe in the liquid, in the gas phase, and they are in equilibrium at a certain temperature T, which is the evaporation temperature for that particular pressure. And of course, you have a system where the temperature is the same, and the particles can move from the gas phase to the liquid phase. Okay, and so clearly, this type of description is not appropriate for those type of systems, and you better use this type of system, but this type of description. But there are also other cases where this description is much more useful, because even if the number of particles is fixed, computing the partition function may be difficult for a fixed number of particles. So it might be more practical to compute to derive the properties of a system with a fixed number of particles from the property of the system where the number of particles can fluctuate. And we are going to see examples of this, in particular quantum ideal gases. Okay? Okay, so what is the system that we are considering? So we are considering a system which is in equilibrium with a much larger system. So we consider system A, which has a certain energy E and a certain number of particles N. But these are this is in contact, both thermal and chemical contact, with a much larger system, which we call the heat bath. In this case, it's a heat bath for which also allows for exchange of particles. And now we want to compute the probability. So this system A can be in a certain number of states R. There will be a certain number of states of the system A, which I will label with R. Each of these states will have a particular energy ER and a certain number of particles NR. And I want to know what is the probability of a state R. In particular, what is the probability to find a state, the probability to find this system A in this state. And okay, so we know how to derive the properties of the combined system A and A prime, because this is an isolated system. And we know so that the energy of the combined system will be the energy of A, which we call ER, for if the system is in state R, and the energy of the heat bath. And we also know that the number of particles for the combined system will also be conserved, and this will be the number of particles of the system A plus the number of particles of the system of the heat bath. Okay. Now, the probability to find the combined system in a state with this energy and this number in a particular state is proportional. So the probability to find a combined system in a microstate with energy E0 and number of particles N0 is equal to the number of microstate of the combined system. Now, if I'm going to fix the state of the system A, the probability to find the combined system in this particular macrostate is going to be proportional to the number of ways in which I can find the heat bath in a state with energy E prime and N prime. Okay. And then the probability to find my system in a state R with this energy and number of particles will be proportional to the probability to find a global system in this state with these energies. Okay. So this probability will be proportional to the number of microstate of the heat bath with energy E0 minus ER and number of particles N0 minus NR. Okay. Now again, I'm considering the case where the heat bath is much larger than my system. So in particular, I'm considering the case where ER is much less than the total energy of the system. The number of particles is much less than the total number of particles in the system. So what I can do is to make an expansion for around E0 for a small value of ER and NR. Okay. So rather than doing on omega itself, it's better to do it on the log of omega. So log of omega prime of E0 minus ER and N0 minus NR will be equal to log of omega prime of E0 N0. And then there is the first derivative, which is the derivative of the log of omega prime with respect to E prime, computed in E prime equal to E0, times the change, which is minus ER, plus the derivative of the log of omega prime with respect to the number of particles of the reservoir computed in N prime equal to N0 times minus NR. Okay? Now, so you see now we know that we know the interpretation of these things from the canonical ensemble. So we know that from the microcanonical ensemble. So we know that this will be the entropy of the will be proportional to the entropy of the heat bath. This will be related to the temperature of the heat bath, and this will be related to the chemical potential of the heat bath. Okay, so what we find from this is that the log of probability to find the system in a state PR will be equal to a constant plus well, minus this is 1 over so we know that K times the log of omega is the entropy, and the derivative of the entropy with respect to the energy is 1 over the temperature, so this is 1 over KT times the energy ER. And then we know that the derivative of the log of the derivative of the entropy with respect to N is minus the chemical potential divided by T. And so, so we know that this will be plus mu divided by KT times NR. Okay? So from this, it follows that, and this constant will be just determined by the normalization, because if I sum over all the states, the probability has to be 1. Okay? So the probability in the grand canonical ensemble is of a state with energy ER and number of particles NR is given by mu divided by KT times NR plus ER over KT divided by the sum over all the states e to the mu over KT. Prime, sorry, there is a minus here, minus ER prime over KT. Okay, so this is the grand canonical distribution. Okay. And of course, you see here I've considered only the first term in the expansion. The other terms in the expansion, so there will be another term in the expansion here which will be proportional to derivative of the log of omega squared divided by the for example, dA squared times ER squared, for example. Now, this is proportional to the entropy. This is proportional to the energy squared. So this term will be proportional to 1 over the size of the heat bath. Okay? So, so this term here will be proportional to the, if you want, to the volume of the 1 over the volume of the heat bath times essentially the energy of my system, which is essentially proportional to the volume squared of my system. Okay, so you see this term compared to this is of order the volume, the size, the ratio between the size of the system and the size of the heat bath. So when the size of the heat bath is very, very large, goes to infinity, all these terms disappear. Okay? So all these other terms are irrelevant. And then we get these results. Questions? Yep.
We start by saying that probability is proportional to probability for the heat bath having energy private.
Yeah.
Can we write an expression for the proportionality?
Yes, usually when you think about probabilities, there is always an easy way to find the proportionality constant, which is by normalization. Okay, so it's so the constant is always given by the normalization, so that you can, of course, I mean, you can think of doing a more detailed study. So in particular, yes, again, if you say that the probability is proportional, as we have said, to omega prime of E0 minus ER. Okay, let me forget about n. Then, if you want to replace this proportionality by an equal sign, then you can always do this. Divide by the sum over R prime of E0 minus ER. Okay? And this is going to be the total number of microstate of the combined system, right? So.
Is this argument always true? I mean, you may have any degrees of freedom or states for the heat box. So
Yes.
just to say that for our system, the probability is just proportional to the.
So the
I mean, when is this thing valid? Like saying it is proportional to the probability of having the heat bars with energy private and particle.
Yeah, so the argument which I'm using here is to say I want to fix a particular state R of my system, and I want to compute the probability of this state, okay? So in the microcanonical ensemble, it is easy, no? Because either the energy is ER is equal to the energy of the system, and the number of particles NR is equal to the number of particles of the system, and then the probability is 1 over the number of states. Or if it is different, it's 0. If the energy is not the energy of the system and the number of particles, then it's 0. Here, essentially, it is more complicated because the energy of my system and the number of particles of my system can vary, okay, from 0 to infinity. So, but of course, I mean, you imagine this. So, if you look at a system where the number of particles is very, very small, so, or there is no particle inside here, then this would correspond to a very unlikely state of the whole system, right? So in particular, it will correspond to a very unlikely state of the reservoir, of the heat reservoir. Okay. So you see that the probability, in order to assess what is the probability of the system R to be in a state R, you have to consider the combined system. Okay. Because you know that the states of the combined system will be uniform, will be equiprobable. Okay. Then you have to, if you fix a state for the system A, you have to compute how many possible microstates are accessible to the rest of the system, right? And the probability of that state will be proportional to that. Okay. So, so this is the argument. I mean, if you think about it, in order to compute this probability, we have again we again went back to the microcanonical ensemble, where we assume, by assumption, by the ergodic assumption, that all the microstates are equiprobable. And then from that, we derive this result. Okay. Okay.
This surely changes if the system A is moving. That's the system was
So if the system A is moving. Okay, so again, as I told you, we are discussing equilibrium statistical mechanics. So if the system is moving, then there are a number of complications. In particular, I mean, the system, the description of this system which is moving inside another system is much more complicated than this, because it is a non-equilibrium system. Okay, and so in particular, yes, in the description you will have other variables which become important. So, what is the total momentum of the system? What is the total angular momentum of the system A, etc., etc. Okay, so we are not considering these problems here. Okay. Okay, so what I would like to do now is to rederive this result, but from a different perspective. That is from the perspective of ensembles. So as we said, we can think of all we need in order to compute physical quantities is to have a distribution over the possible microstate of the system over which to compute statistical averages. Okay, so we would like to and the way we think about this distribution is that for any possible microstate of my system R, the way we think about this this average is over a population of identical copies of the system, which are distributed on the possible microstate of the system A. Okay, so. Sorry?
If the two systems are moving with the same velocity, it's like we do nothing on the motion.
Yes.
So in this case, can we talk about
Yes. So we are talking about systems which are not in relative motion, or where the parts are not in relative motion with respect one with respect to the other. Okay. So. Of course, you can always think, I mean, every equilibrium system will be in some reference frame which is moving with respect to another reference frame. So, but.
the case I'm talking about is the two systems are moving with the same velocity.
Yes.
So it's in mechanics, it's like we do nothing.
Yes.
So can we have the same
Yes, so you can think of applying all we are saying two systems where there are no parts in relative motion, one respect to the other. Okay? So if my system A is in motion with respect to the heat bath, then you cannot think it is a system which is in equilibrium, in thermal equilibrium, because there is a relative motion between the heat bath and the system. Okay? If they are both moving, then with the same velocity, then it's just a Galilean transformation, and you can always describe things with respect to the reference frame where they are not in motion. Okay. Okay. So and okay. So the way I would like to think now about my system is in terms of ensembles. And an ensemble for me is equal to a population of systems distributed on all possible states. Okay, so it's n. It corresponds to n copies of the system. Well, this n will be very large, and eventually will go to infinity. These are identical copies. They don't interact. And I would say that there are nr of these copies in state R. Now I want to define this ensemble, the grand canonical ensemble, for the case where my system does not have an energy which is fixed and does not have a number of particles which is fixed. Okay. Rather, what I want to say is that the average number of particles will be fixed, and will be given by something. No, because I mean, physically, if you observe your system, which is in thermal equilibrium with another system, is exchanging particles, still there will be a certain average number of particles in this system. So we want that this average number be essentially the average over this population of the number of particles in the state R, and the energy will also be fixed. So the average energy will also be given. Okay. So every so a microstate is equivalent to an assignment of the population of copies of the system in my ensemble on the states of the system, such that these two conditions are satisfied. Okay, so all these microstates will be consistent with a macroscopic state where the number of variables will on average be this, and the expected the energy will on average be this. Okay. Now we can essentially do the same calculation which we have done for the canonical ensemble, and so for any assignment of this, for any distribution of the copies of my system on the states, there will be so for any distribution n R, there will be a number of microstates which is equal to n factorial divided by, because essentially you have to think about the ensemble as a gas of non-identical particles which are distributed on the possible states of the system. Okay, so actually yes, so if you want, a microstate is not defined by an R, but is defined by in which state is my copy number 1, in which case state is copy number 2, and in which state is copy number n. Okay, so a microstate will be an assignment of each of the copies in my ensemble to a particular state, and so this would correspond to a certain NR, occupation number of the states, and there will be these many microstates which have the same occupation number. Yes? So NR is the number of systems, of copies of the system which are in state R in the ensemble. Okay? You can think of, if you want to, you can think of phase space, on the phase space. So each of these points, each of these state R correspond to a cell in the phase space. And NR would correspond to the number of the number of copies of the system of the ensemble which are in this cell. Okay, is an occupation number in phase space. Okay, so this n is the number of particles. Okay, this is the number of particles of state R. This n curly is the total number of copies. Okay, so and this is the number of copies of in the ensemble which are in state R. So of course you have the sum over R of this NR is equal to this curly n. Okay, so that the probability to be in a the probability that one copy is in state R is NR over n. Okay. Now, so all the so for any microstate, so what I have to do is to consider microstate for which essentially the number of particles and the energy is fixed. So if you want, for any microstate, you have to consider microstates such that this is so this is the number of particles in state RL, and I'm summing over all the systems, all the copies in my ensemble, and I'm taking the average. Okay, so this would be the average of the number of particles in the ensemble. So I have to take all the assignments of copies of my systems such that this is true, and all the assignment of my system such that this is true this is the average energy in the ensemble, okay? And these essentially will constitute my ensemble, no? Because in principle, each of these microstates should be equally probable. Okay. Now, the important observation is that the number of microstates with a given occupation number in the state of all possible states of my system is given by this, and it will be it is a huge number. It will be dominated by the maximum, okay, as in the canonical ensemble. Okay, so what I can do is to look at the n star such that the W of nr is maximal, subject to these two conditions. Okay. Okay. So, and essentially, as in the canonical ensemble, what I will find is that almost all microstates will have an occupation number which is equal to this nr star, because this is a quantity which is very, very sharply picked on n of r star. Okay, so so how do we do this this calculation? Again, this is just constrained optimization. So if you want to maximize this object subject to those two constraints, essentially what you have to consider is a problem where you want to find the extrema of something which is convenient to take the log of this. You want to find the maximum of W of log of W of nr plus you have to put two Lagrange multiplier, alpha times sum over r nr times nr plus beta sum over r nr times er. Okay. So this is the problem that you have to solve. You can use the Stirling approximation to compute this, and then this is n log n minus sum over r nr log of nr. So when you do this, then you take the first derivative of this expression with respect to nr, and you have that minus log of nr plus alpha times nr plus beta times nr, and then you have times er, sorry. And then you have minus 1. This must be equal to Well, and then you have another Lagrange multiplier which you have to add here because you want to find those so you have to constrain to the fact that the sum over the NR should be the total number of copies. Okay, so you will have another constant here. This will be equal to 0. Then you see that the solution of to this will be that NR is equal to a constant times e to the alpha NR plus beta ER. Okay? And now you have to fix this parameter alpha and beta in such a way to satisfy the two constraints on the number of particles and the number of and the average energy. So this constant C in such a way that the sum overall R of this is equal to big N, to curly N. And but you see that the functional form that you get from this is that the probability distribution of a state is essentially exactly what we have derived previously, with alpha, which is which in the previous case we found was chemical potential divided by kT, and beta, which was in that case 1 over kT. And then you should have the normalization constants, okay, of the same thing. Okay? So you see even from the point of view of ensembles, you obtain the same result, that the probability distribution which describes ensemble of points in the phase space or in the space of states of your system, which is consistent with fixing the energy, the energy and the number of particles, the average energy and the average number of particles, is given by this formula. Okay, now we want to make a connection with the thermodynamics. How do we relate this to thermodynamics? To thermodynamics. In other words, we want to find the analog of a partition function, which allow us to compute a thermodynamic potential from which we can compute thermodynamics. Okay, so and we have seen that the probability of a state R is equal to e to the minus, let me call it alpha NR minus beta ER. Divide, actually, let me take, as in the book, minus alpha also here. And with somewhere R prime e to the minus alpha and R prime minus beta E R prime. Now, what I would like to do is So we have seen that in the canonical ensemble, this was the partition function. What we had at the numerator, the denominator was the partition function. And the partition function was what was playing the role of the number of microstates. So if I took the log of this, then that was related to the thermodynamic potential. Okay, so let's do the same thing. Okay, let's take as a guess this object, which I will call grand partition function, which is the sum over all the states of e to the minus alpha n of r minus beta e of r. And let us consider the log of this object here. In particular, let me consider the differential of the log of z. Now, if I take the differential, so what does z depends on? It depends on alpha, it depends on beta, and it also depends on the energy levels of my system. Okay? And so if I take the differential, there are three parts. So one is when I take the differential with respect to alpha. So here I will have 1 over z. Above I will have sum over alpha, sum over r, n r e to the minus alpha times n r times d alpha. This is the differential with respect to alpha. If I take the differential with respect to beta, I will have minus the same thing with ER e to the minus, oh sorry, there is minus beta ER, of course. Minus alpha and R minus beta R divided by Z times d beta. And then there is the change in the energy levels. So which is which will be equal to minus the sum over R times 1 over zeta times the beta times d e r times e to the minus alpha and r minus beta e r. Oh, sorry, there is a minus. Okay, so there are these three terms, which I can rewrite in the following way. So this is clearly the average number of particles. This is the average energy. And what is this object? So the first term is minus average number of particles times d alpha minus average energy times d beta. Now this object here, you see there is a beta, and is somewhere r of this object divided by z is actually the probability of the state is exactly the probability of the state R. So this is the sum over R of the probability of state R times DER. Now this is minus this object is exactly the work which is done on the system. So when I do work on the system, what happens is that I modify the potential energy of the system, or and then there is a change. This results in a change in the energy levels of my system. Okay, so this term is exactly the mechanical work which is done on the system. Okay, so given this, I can write that d log z is equal to minus n times d alpha minus e times d beta plus beta times d work. Now, what I want to do is to find an exact differential for an exact differential from which I could derive thermodynamics. Okay. So this is clearly not an exact differential. So let me now consider the following combination, which is the differential of log z plus alpha times n plus beta times energy. Okay. Now this, so the differential of this is the differential of log z is minus n d alpha minus e d beta plus beta times dw. And then I have the differential of these things, which is alpha dn plus n d alpha plus beta dE plus e d beta. Okay. Now this term and this term cancel, and this term and this term cancel. And now I have beta, which multiplies the work plus the energy. Okay, but I know that from the first law of thermodynamics, I know that the change in energy is the heat, which is TdS, is the heat, minus the work. And then there is the chemical work, which is mu dN. Okay? So that dE plus, sorry, this is dW, the work. Okay? So that dE, dW plus dE is equal to TdS plus mu dN. TdS plus mu dN. Okay? And so this is this and this, and what I'm left is just this alpha times dN. Now, if I want this to be an exact differential, then so in order for it to be an exact differential, we must have that this term and this term cancel, and this should be a constant. Beta times t should be a constant. Okay? So for this to be an exact differential, we should have that beta times mu is equal to minus alpha, and that beta times t is a constant, which I can call 1 over, which I can decide it to be 1 over Boltzmann constant. Okay? And then, yeah?
When we say that we fix the average number of particles N
Yep.
and the average energy E, right?
Yes.
Then the N bar and the N E bar, then there will be, I think, 0.
So, Yeah, so what I'm thinking here is, yes, I'm thinking at an infinitesimal transformation of my system. Okay, so the most general infinitesimal transformation of my system, and then I'm looking at how will this object change. Okay, so this is does this answer to? This is this tells us how this quantity changes. If you make so, you have to think. In this case, you have to think at alpha and beta as external parameters, and so this tells you how in general this quantity log z will change. And then now we are using this to look for an exact differential. And
That expression is okay because but my concern is here. Okay, you say the average is just a number, it's just a constant.
yeah.
Then thinking about an infinitesimal transformation, then what does it mean? I mean, if it is there, if it's a number, if it's a constant, then the differential will be
Yes.
zero.
Yes. So indeed, yes, there is no. So, for example, you see, we have considered the work, which comes from the fact that if you do a transformation, you can change the energy levels. You don't change the number of particles.
Yeah,
Okay.
Alpha d
Yeah.
bar, beta d bar will be
Yeah.
equals 0.
Yeah. Okay. So so that if we do this, if we take this choice, then we have out of this an exact differential, which is that so that this is just ds over k. Okay. So this tells us that S over K, the entropy divided by K, is equal to log Z plus, well, alpha, we said that is equal to minus mu over KT times N plus beta energy divided by KT. Okay, so that so we can relate log Z we can say that log Z, say KT times log Z is equal to T times S plus mu times N minus E. Okay, so now there is a general thermodynamic relation which tell us that this is exactly equal to minus PV. So minus or plus. So let's derive it. So the general thermodynamic relation is so you have the entropy, which is a function of number of particles, volume, and energy. And you know that the entropy must be extensive quantity. Okay, so you should satisfy this equation here. Lambda E. Okay, so if I take the entropy a system and I multiply the number of particles by the number of particles, the volume, and the energy by lambda, then you should get the same entropy multiplied by lambda. Okay. Now you take this equation and you derive by lambda. take a derivative of by lambda on this side and on this side, and set lambda equal to 1. So if you do this, here you get S. And on this side you get n times the derivative of S with respect to n, which is minus the chemical potential. Here you get the derivative of S with respect to V times V. So you get PV. And here you get the derivative of the entropy with respect to the energy, which is 1 over T times the energy. Okay? So you see that Ts plus mu n minus E is equal to PV. So this is the way in which you derive. So you compute. So the recipe to compute physical properties in the Grand Canonical Ensemble is to compute this Grand Canonical partition function, which is the sum over all the states of E to the mu divided by kt times nr minus er divided by kt. You compute this number, you take the log multiplied by kt, and this is pressure times volume. You get the pressure of the system. And then you can compute all thermodynamics properties. Okay? Now, let us make a couple of examples. So before doing so, let me mention that it is, so this is called the Grand Canonical partition function, and it is useful in many cases to write it in terms of what is called the Fugacity. Minus ER over KT, where the Z is e to the mu divided by KT. It's called Fugacity. And this you can also write it, you can think of writing this in this form. So you first do the sum over all the states. So you split this sum in two parts. First you sum over all the possible number of particles, and you do the sum over all the states with that number of particles. Okay? So you sum from n equal to 0 to infinity. You have Fugacity to the power n. So this is a z. Okay, so a small z to the power n. And then you have the sum over all the states of e to the minus er over kt, where here the sum is over all the states with nr equal to n. But this sum here is precisely the canonical partition function for a system with n particles. So you can write the Grand Canonical partition function as the sum from n equal to 0 to infinity of Fugacity to the n times the canonical partition function to at temperature at volume V and temperature T. Okay. So the recipe is that you compute this number, and then you get the physical properties from this equation. So, yeah. Fugacity, yes. It's a redefinition of.
On the second part here on the explanation, we don't have mu, right?
Sorry. Yeah. Yes, you're right. E to the, yeah. This is an E. So, examples. So let's take non-interacting systems. So if I take non-interacting systems, then the partition function, as we have said, in the canonical partition function is easy to compute. And we can consider two different cases. So the first case is when the particles are indistinguishable. So this was, for example, the case of the ideal gas. So in the case where particles are indistinguishable, then this partition function is 1 over n factorial times the partition function of one particles only to the power n. And typically the partition function of one particle, if there is no potential which is acting on the particle, we think of a gas. So it's just the volume times a function of the temperature. So this is just the volume times a function of the temperature divided by n factorial to the power n. Okay? So then the grand partition function is equal to the sum from n from 0 to infinity of here I have z to the n times q to the n. So I have z times v times f of t all to the n divided by n factorial, right? So, and this is very simple, is e to the z times v times f of t. Okay, so f of t, for example, in the case of the ideal gas, so this f of t for the non-relativistic classic ideal gas was 2 pi m kt over h squared to the 3/2, right? This was the function f of t for the ideal gas. Now you see, so the recipe is that if you take the log of this, so for example, we want to compute the pressure. The pressure is the log of is z is equal to z v times f of t. And so the pressure is equal to kT times this. So it's kT zv times f of t, well, divided by v, so the v goes away. So this is the pressure, and so From this I can compute the expected number of particles. So the number of particles in this system you see, if I take the log of z with respect to the small z, and if I multiply it by z, so what happens is that when I take the derivative of the log of z with respect to z, I get 1 over big Z times the sum over n of n times z to the n minus 1 times qn. And if I multiply by z, I get exactly n times z to the n qn minus 1, which is exactly the expected number of particles. Okay, so this is equal to the expected number of particles. And so in this case, you see the expected number of particles is equal to, if I take the derivative with respect to this, with respect to z, I just get v times f of t. So the expected number of particles is z times v times f of t. So, so what I can do is to use this equation. If I want to describe a system with a finite given number of particles, I can take this equation and solve it for z and get the fugacity as a function of n, and v and t. So this would give me that z is equal to n over v f of t. And now if you put this back here, you see that you get kt times n divided by v. Okay, so you see this is again the ideal gas law. Okay, as it is expected. So you get PV uguale equal to n kt. And if you take, likewise, if you take the derivative of the log of z with respect to beta, or 1 over kt, you get minus the energy. Okay? So this means that in this case, the average energy will be, but this is, you can also write this as the derivative of temperature T with respect to the beta d over dt. So this is kt squared derivative with respect to t of the log of z. Okay. So so if I take so the average energy is k t squared times the derivative of this with respect to t is going to give me z v times f prime of t. And again, if I substitute, if I eliminate the z by using this, I get that the average energy is equal to, so z times v is n by, is equal to k t squared, k t squared n times f prime of t divided by f of t. So you see that if you put here this result, for example, So this is the derivative of f of t, of the log of f of t with respect to t. So this is 3 over t. So you get again that the energy of the ideal gas is 3 nkt, as you should expect. Okay. Now the second example which I want to discuss is the gas of oscillators, which we have discussed. So for a gas, so for a case where instead we have distinguishable particles, for example, the case of n oscillators. You remember we have discussed this problem where we consider, for example, a very, very simple stylized model of a solid, and the solid has atoms on the position of a regular lattice, and our model is that each of these atoms can have a harmonic oscillation around this equilibrium position. And we have assumed that all these oscillations are independent. So it's a gas of, if you want, 3n harmonic oscillators, okay, all with the same frequency. So this is called the Einstein model of oscillation for a solid. So, but in any case, so in this case, we have seen that the partition function for a system at temperature T and volume n. So it has two differences. So one is that there is no 1 over n factorial. And the second thing is that, well, in our case, if we look at this system of n harmonic oscillators, so these do not move. So there is no dependence on the volume. Okay? So the partition function is just given by a function of the temperature to the power n. Okay? And then we can compute the Gram partition function. The Gram partition function is just if I multiply this by z to the n and sum over all the n from 0 to infinity, this is just the geometric series. And the sum is just 1 divided by 1 minus z times phi of t. Okay? Very good. So what is the relation between the fugacity and the number of particles here? So the relation is given by I take the log of this, take the derivative with respect to z, and compute n as z times log of this capital Z. So this is minus z times the derivative with respect to z of log 1 minus z times phi, which is equal to 1 minus z times phi times z times phi. Okay. So if you this tell us that 1 over n is equal to 1 over z phi minus 1. Or z phi is equal to n plus n over n plus 1. Okay? So from right? Now, what is the pressure? So the pressure is equal to, the pressure in this system is equal to kT divided by V times the log of Z times the log of 1 minus Z times phi with a minus sign. So if I substitute Z for N, this is equal to 1 minus Z phi is just 1 over N plus 1. So this is just kT divided by V times the log of N plus 1. So, yes. So you see the pressure essentially is, since when the system is of order 1 over V, so essentially is equal to 0. So the pressure is, this is essentially telling you that the pressure is 0. Because it is a system of particles whose position does not depend on the external forces. Okay? Only the oscillations depend on the external forces. And likewise, you can compute, for example, the energy. And the energy is, so the energy of the system is kT squared, the derivative of the log of z with respect to the log of 1 over z phi with respect to t. So when you take this derivative, this is kt squared, and there is 1 minus z phi of t times z times phi prime of t. Right? Now, if you use the relation which I've just erased, so that z phi is equal to n divided by n plus 1, you have that this is equal to k t squared times n times phi prime of t divided by phi of t. Again, say for the, if we consider a gas of harmonic oscillators, yeah? Sorry? Why this is 0? Eh? Because, so this is an intensive parameter, kT is intensive. This V is extensive, okay? So the pressure is inversely proportional, well, and the log is small compared to an extensive parameter, okay? So this is proportional to 1 over an extensive quantity. Yes, but it grows much less than than linear. The log is very, very, very small. So take, so n in a gas is 10 to the 23, okay? So the log of n is 23, divided by, times the log of 10, okay? So it's 50, okay? 50 compared to a number with 23 zero is 0, essentially, okay? Okay, so here you have to think that this pressure is proportional to, so the volume will be proportional to the number of particles. So this is kT divided by something which is 10 to the 23 times the specific volume of a single particle times the log of this, which is a small number, okay? So the pressure is essentially 0, okay? Which makes sense because this partition function does not depend on V. So the pressure would be exactly 0 in the canonical ensemble. Because so you see, if you take the canonical ensemble, you fix the number of particles, then the pressure is exactly 0. And the grand canonical ensemble, it is not, because the number of particles can fluctuate. Okay, so there is a small correction. Now for the gas of so this is the average, so we have said that the average energy is equal to kT squared times average number of particles times phi prime of t divided by phi of t. And so for a gas of classical oscillators, you get that this phi of t, as we have said, is kT divided by h bar omega. And if you have 3 degrees of freedom for each particle, this is to the cube. Okay? So you see, if you take phi prime over phi, then this gives you exactly 3 kT times n for a gas of classical harmonic oscillators. Okay, if you take this function here and put it here, so this. Now, okay, so I think this is a good place where to stop.